Yo, what's up, folks? uh, here, um, Here is a place where we're introducing a big concept of power. Energy we've talked about. We'll talk about electrical energy and how to calculate that. But that's going to come actually from this idea of power. Now, power is something that you can introduce during our energy unit, of course. Um, but it works pretty well to do it here as well. Well, by definition, power is the rate of, well, one way to say it is energy consumption. Another way you could say it is energy transformation. Another way to say it is rate of work. Rate of work, I don't like that, but rate at which work is done. Okay, now rate always means, for us, per unit time. All right, so that means that power is, we can write it as this. It's more common to see it written like that, the rate at which work is done. All right, and if we were to go, I mean, this we could put right into our unit of work and energy, right? Where we say that work is F times D, or work is, delta E total. I can even put that in here, delta E total. Okay. So now there's one way to connect work with this unit, which is to say that work is Q times delta V. Might remember that from electrostatics. Well, we're here. Our delta V just is voltage. So we don't really need that delta V. Okay, so sometimes we'll write this, or if we want to do a little derivation, we can say that power is QV over T. Why did I drop the delta? Because we just mean voltage. So we've been using plain old capital V for voltage. All right, well, in here lies another formula. One of you asked me a couple weeks ago, are we going to have to know that formula for this quiz? Charge per unit time is an expression for electrical current, all right, which means we can write power as current times voltage. All right, one equation for power. A big one in this unit at least. I mean, these are certainly, this is a big one, typically in different units in the energy and work unit. And sort of same thing here. All right, now, it's pretty common to write this in some other ways because we can say, using Ohm's law, V is I times R. So we have here I times R, right? I times R. Well, that's I squared R. So there's another expression for power. We could also say, well, I is V divided by R per Ohm's law. So we could do V divided by R times V. A third expression for power is V squared over R. Okay? Those are three big expressions to find electrical power. Or the power we say dissipated or consumed by an electrical circuit. Okay, so for sure, let's be okay with the fact that power, well, at its most fundamental, if we look here, power is measured in joules per second, and a joule per second is what we call a watt. So we abbreviate power. We abbreviate the unit for power as W's, watts. Don't get mixed up with this W for work and this W for watts. One's a variable, one's a unit. Okay, those are units for power. Now, energy, if we go right from here, this means that energy is just power times time. So we can talk about how much energy something consumes if we know how much power it dissipates and how much time it's been doing that. All right, so this, of course, could be, energy could be I V T. It could be I squared RT. It could be V squared over R times T. All right, as long as you know this one, and yes, these three, then you can get to all of these. Okay? Fair enough? Now also, energy up here, you'll notice, right? Well, just measured in joules over here. Energy measured in joules, right? Joules per second times seconds to joule, of course. You also see, you might have heard of this thing called a kilowatt hour. Right? On the bill I pay, National Grid, the power company, I'm charged for a certain number of dollars per kilowatt hour, or a certain number of cents per kilowatt hour. Well, a kilowatt hour, notice, kilowatts is a measure of power, hours is a measure of time. So we're doing this, power times time. They're charging me a certain number of dollars per unit of energy. So a kilowatt hour is not a joule, but it's like a joule in that they're both units of energy. Okay? But for us, when we deal with, what do you call them, with energies, we'll deal with energies in joules. Okay? Okay. A couple of applications here. We've got two circuits. Now yours in your notes probably have values for those voltages, but let's pretend they didn't. All right. The question is, which resistor uses the most power? Well, we have three different resistors. We don't know what the drop is across any of them. We don't know what the current is, but we do know that there's the same, since these are in series, there's the same current through each one. All right? Now, we have three ways to look at power. I times V, I squared over R, or V squared over R. So if there's the same current in each one, and I look at this one, well, I don't even have to worry about what current is. It's the same for everything. This just says the bigger the resistance, the more power. All right, so that means over here, the 150 ohm uses the most power. So I'll say at same current, power is proportional to resistance. Okay? Now over here, which one uses the same or the most power? Well, is it just the biggest resistance again? Well, the deal over here is that these don't have the same current, but they do have the same voltage. Same voltage drop. All right, so that can almost lead me to this one, where if the voltages are all the same, who cares what they are? So I'm going to say here, at the same voltage, power is proportional to, well, the inverse of R. So this says that the smallest resistance gives us the biggest power. And that means the 5 ohm uses the most power here. Okay, so obviously a big difference between things that are connected in series and things that are connected in parallel. All right, what I'd like you to do as part of your homework is calculate power dissipated by each resistor in both circuits. Yes? Yes. Do. Next. Let's see. Yeah. Okay. So, I remember this from a test. I took this test several years ago for part of my teacher certification thing, and this was on it. It said there are 3 light bulbs that are identical, and this is a big deal. We're going to start to talk, we'll do some talking about light bulbs, and light bulb brightness depends on how much power they dissipate. Okay, and you have these 3 bulbs connected as you see, all right, A, B, and C, and then and then the question is, if we unscrew bulb B, what happens to the brightness of the other 2? All right, so I want you to answer that question. Okay, and there are a couple ways to do it. One is to think through it without numbers, but you can sort of think through things like, okay, if I unscrewed this one, then the resistance of this thing would do that, and that would make the current here do this, and then the voltage drop there might do that, and okay, then the power would, so you can sort of think through it like that, or if you want, I mean, just make up some numbers. That's kind of the more boring way, in my mind. I'm being a snob, but if you want to make up some numbers for all these things, feel free. All right. What else? And here's another problem in the bottom. And the problem here says, what would happen to the brightness of all the bulbs, or sorry, of C, if bulb B was shorted out? And shorted out means that we just take a wire and connect it like that. All right? A short is a case where current that gets here has 2 options, but why would any of it go through here if there's resistance there? Current, flows, well, inversely proportionally to resistance. So if this wire has quote-unquote 0 resistance, then all current will go through there. Okay? So tell me what happens, multiple choice, to the each of those bulbs, the brightness of each of those bulbs, if the bulb is shorted out. Now, for this one, do you need work? I don't know. For this one, I got to see something, all right? I can't have you come in and say, well, I just thought about it and I think it's C. I want to see something. All right, I want to see something in terms of, how you came up with your answer. Okay? What I didn't say is back on this page, if you don't have the notes, I think this was a 20-volt source, and I think this was a 50-volt source here. All right, so when you're finding those powers dissipated by all the resistors, by each resistor, you do need a voltage, a source voltage. Okay? That's it. We'll get into which bulb is the brightest tomorrow, or Wednesday. Thursday we have a quiz. That quiz is on stuff like this. Complex circuits, and also stuff like this, combination circuits. That's Thursday quiz, okay? All right, folks. Yeah, good. See you tomorrow.